Hello everyone, I'm Iftikhar. Today I'm going to present our work DDS, Decoupled Dynamic Syngraph Generation Network. Our goal in this work is to predict relationship triplets under compositional setting. At each frame of an input video, we want to predict subject-object relationship triplet as shown on the screen. But what do we mean by compositional setting? Let's define that first. Imagine we have m number of relations and n number of objects. In total, we can have m into n number of relation object composition. This set is represented by KT. Under compositional setting, we need to detect relationship triplets from this set KT. But our training only has b number of relation object composition. This set is represented by Kn. Set Kn is much smaller than set Kt. Before deep diving into DDS, let's have a look in the existing works. These works are almost exclusively built for fully supervised setting. They are composed of two stages. In the first stage, an object detection network detects objects in each frame of the input video. In the second stage, a spatiotemporal network utilizes features from the detected objects for scene graph generation. While these works have achieved state-of-the-art performances in the fully supervised setting, we observed they perform poorly when detecting relationship triplets outside of the relation object composition seen during training. There are two key aspects behind this performance degradation. Existing works use same features for object relationship detection. As a result, these networks learn to associate relationship with specific subjects and objects. We circumvent these limitations with the key concept of decoupled learning. Here, we show the core idea behind our work. We want to ensure our network learns different features for objects and relationships. While object and relationship features are dependent with each other in a scene, the essential cues for detecting objects and relationships are a bit different. This decoupled learning helps us to transfer learned concepts to identify unknown relationship triplet. As shown, our network understands the action right, the objects human, dog, bicycle. Therefore, it can easily transfer the learned concept to detect the unusual action of a dog riding a bicycle. Now, let's see how we implement the core idea of decoupled learning. Our network is consisted of two mirrored branches, one for the object detection and the other one is for the relationship detection. From the input video, we extract features using convolutional backbone. These features are sent through our object and relationship branches. Both these branches have an encoder and a spatiotemporal decoder. Encoder encodes the extracted convolutional features, while decoder utilizes the learnable queries to learn from the encoded features. Finally, the object and the relationship heads predict the relationship triplets using the decoded queries. One thing to note here is that after the feature extraction, the object and the relationship branch process the features in a decoupled manner. This design ensures the independent learning of the concepts. Therefore, our network can successfully detect unknown relationship triplets. Next, we will discuss about the different components of our network. For feature extraction, we use a convolutional backbone like ResNet. The convolutional features are flattened and fed to the self-attention block in the encoders of our mirror branches. The encoders identify spatial relations among different spatial positions. The output of the mentioned encoders, along with the learnable queries, are fed to our decoders. They are consisted of two components, temporal and spatial. In the temporal decoder, the learnable queries first attend to the previous frame's embedding to learn about the temporal correlations. Next, the queries attend to the encoded features. This attention mechanism helps the queries to learn about the objects and relationships present in the current frame. The output of the decoders are the learned queries that will be used by the object and relationship heads. Finally, we utilize the feed-forward networks presented as FFN in the slide to predict subject class, subject bounding box, object class, object bounding box, relationship class, and relationship bounding box. The object head takes learned query from the object branch as input, and the relationship head takes the learned query from the relationship branch. The relationship bounding box is defined as the union of subject and object bounding box. This is basically an empirical choice. We want to reiterate the key innovation of our work is the decoupled processing of relationship and object features that help us to generalize towards unknown concepts. To show the effectiveness of our network, we have evaluated it in three standard benchmark datasets: Action Genome, Hecodate, and Unreal datasets. Among these datasets, the commonly used Action Genome dataset doesn't have any compositional split. So we created a compositional split for ourselves to evaluate DDS under compositional setting. This split is mentioned in the second row of the table. For our evaluation, we considered a prediction is correct if the predicted subject and object bounding boxes have IOU greater than 0.5 with ground truth bounding boxes, and also predicted subject, object, and relationship labels match with the ground truth labels. For different dataset, we have used different metrics according to the benchmarks. Now let's see DDS's performance under the compositional setting. In AG compositional dataset, DDS outperformed the SOTA model STTRAN by 34%. If you noticed, in the unseen class, DDS's performance improvement is much bigger. In Hecodate dataset, we achieved a performance gain of 5%, and in the Unreal dataset, we have achieved a performance improvement of 33%. In all these benchmarks, DDS has shown much improved performance, especially while detecting the unseen relationship triplets. In the full supervised setting, DDS has achieved comparable performance with the state-of-the-art models. Let's see how DDS perform in reality. So here we have some very unusual examples. These examples are taken from the Unreal dataset. As you can see, these relationship triplets are not very common. And all the compared networks, all the state-of-the-art model has failed to identify these relationship triplets. But our decoupled learning has made DDS capable of detecting these unusual triplets. Here we have demonstrated attention map from DDS and compared it with a Bayes network. As you can see, even while detecting very unusual examples, DDS's attention maps are much more defined and focus on the salient regions. In summary, we have proposed a decoupled learning network for generating scene graphs under compositional setting. Our network has achieved state-of-the-art performances in all the benchmark datasets. Thank you. If you have any question, feel free to ask us.